My name is Honor Pius, and in this video we'll be looking at IMO 2022 problem 1. Okay, so there's a combinatorics problem. Alright, so it goes like this. The Bank of Oslo issues two types of coins, aluminium, which we'll denote as A, and bronze, which we'll denote as B. And we have a total of n aluminium coins and n bronze coins, and they are arranged in a row in a random order initially. So now a chain is a subsequence of consecutive coins of the same type. Now given a fixed positive integer k less than or equal to 2n, so we repeatedly perform the following operation. So we take the longest chain that contains the kth coin from the left and move all the coins in that chain to the left end of the row. So here's an example to describe the process. So for instance, n equal to 4 and k equal to 4, meaning we have 4 aluminium coins from 4 bronze coins. So pick a random ordering, for example AA, BBB, A, BA. So k equal to 4, meaning from the left look at the 4th coin. Alright, so this is the 4th position. Then we see that this is a B coin, meaning we can take the whole, this is the longest chain containing B. We take this and place it on the extreme left, so like this, and then we see that the A's will merge here to form 3 A's now, and we have this new arrangement. We just repeat the same process again with the same k, so k is fixed. So we have 4th, and then you see that we take the whole of this chain, so take the longest chain each time and take it to the extreme left. So we just repeat this, and from here we see that at some point after we identify the coin and take the chain, we see that once we take it to the extreme left, we don't get anything new because it's already at the left end. So the question now is to find all pairs n and k such that no matter which initial ordering we are given, at some point we end up in this same scenario, in the sense that the leftmost, that during the process the leftmost n coin will be of the same type. Okay, so let's take a look at the solution. Now we are going to define Ci to be the number of chains, of longest chains. In the height arrangement. So in the sense that the initial one we're given will be the first arrangement, and then we have subsequent ones. Okay, so we observe that each time we make a move, that the next value, the number of longest chains, is going to either remain the same or is going to end up decreasing. So what happens each time we make a move? We end up removing a string of coins of the same type to the end. So there are two ways which we can have some coins merging. So for example, we can have the coins merging when we have A and B. When we have B in between two A's, once we remove the B, we see that the A are going to merge. And also, if we take the coin to the end, it's possible it might also merge with some other string or chain. So the main idea is that it can never increase because we never get to split any of the chains. So at most we could possibly end up merging some coins or remain the same. So this is less than or equal to Ci. So that means that Ci is a decreasing sequence. It doesn't have to be strict. And since we are counting a number of chains, certainly we have to have at least 2 chains, one for A, one for B. So we have that this is greater than or equal to 2. So that means CI is bounded. So we get a decreasing bounded sequence, meaning that it's going to have a limit. And since we are dealing with discrete sets, it means that we have that CI tends to some integer greater than 2 as I tend to infinity, right? So the essence of this is that there's going to be a value greater than or equal to 1 such that CI naught is equal to C and CI is equal to C for every subsequent I. So that's the limit. Okay, so this is going to be of interest to us because we want to see what happens eventually, and since we have a limit, at that point we could say things have kind of stabilized, and then that would be the best place to analyze what is actually going on. Okay, so now we're going to present the answer. So our claim is that the values of k that we're interested in lies in this range and only in this range. So these are any pair where we have this is what we claim to be the solution. Okay, so I'm going to prove this. So we're going to take this in 3 parts. So first of all, if k is less than n, so we want to show that since it's not in this range, we want to show that at some point we never get the conclusion we want. So we're just going to give a counter example. Why is this enough to give a counter example? That's because of this. For every initial ordering, so the opposite of this would be that there's an initial ordering that even after we continue this process indefinitely, we never get the leftmost n coin to be of the same type. Okay, so that means there's going to be a counter example, a time where this doesn't happen. So we're going to provide that example now. Alright, so consider the initial arrangement. We'll have say A, so a chain of A. You have n minus 1 of them, and then chain of B with all the B's, and then the final A, so just 1. So this we've used all n A coin and n B coins. Alright, so from this we see that since k is less than n, the kth position is going to fall somewhere along this chain, and we see that means that the longest chain that it will contain would be this chain, which is already at the leftmost end. So if we pick this chain and place it at the leftmost end, we don't get anything new because it's already at the leftmost end. So this means that we just have the same set of the same arrangement every time, and this clearly doesn't satisfy the condition we would like. So this is fails. Okay, so next, if we have k greater than or equal to 3n over 2 plus 1. Okay, so this also lies outside our range. So we want to provide another counter example for this. So this time we take this arrangement, initial arrangement, where there are n over 2, take the floor of that. Then we have b n over 2, a, so the rest of it, which will be the ceiling. So we have the ceiling and the floor, n over 2. Okay, so we want to show that if we have this, then this will also fail, meaning we never get to achieve n string at the leftmost end. Okay, so what we're going to first do is to show that each time we make a move, that we're just going to end up shifting, rotating this chain by one step. Okay, so let's call this first chain T1, let's call this T2, T3, T4. So initially we have T1, T2, T3, T4. So I want to show that we're going to just end up having a structure like this. T2, T3, T4, T1, and then it's going to come back here. So just going to rotate around 4 states, and for each of these states, once we can show this, each of these states clearly we don't have string of n, a chain of n at the leftmost part, because each of these will occupy leftmost part at some point and their lengths are not equal to n. Okay, so now so we have that. So for this diagram to work, we just need to ensure that each time the kth position is going to land on the chain at the right end. So each time we want to ensure that the chain we're going to pick is going to be precisely the one at the right end. So it's just a matter of calculating their lengths and getting the right position. Okay, so we see that if we have a chain at the right end, let's say an A chain, doesn't have to be A, at the right end, where this is 2n position. Okay, to make sure that this is going to be picked, we need to have at some point k. So this chain might be more longer than this, right? But we need to make sure that the kth position lands at least on A. So meaning that we need to have at least this many A's, and once we have this many A's, it's going to happen. So if we have this to be k, we can actually get the precise number of A we require here. That will be 2n minus k plus 1. So if we can show that all the lengths of T1, T2, T3, T4 satisfy at least this much, then we are done. The least length we could see here is where we take the floor, so we only need to show that the floor of this, so this is what we require to prove, is greater or equal to 2n minus k plus 1. Okay, so now we have that from the inequality, the case we are dealing with, we have that 2n minus k plus 1 is going to be less than or equal to 2n minus 3n over 2 plus 1 plus 1. And if we expand this, just going to get that this is less than or equal to n over 2. Okay, so we can now take the floor of both sides, and then since the left hand side is already an integer, we have this, and then we get the desired result. Okay, so this we've shown for what happens outside of this range. Now we need to show that anything else which is in this range is going to actually work out, meaning eventually we get n of a particular type on the left. Okay, so we'll look at this in 2 cases. So this is the final one. If k is between n and strictly less than 3n over 2 plus 1. Okay, so case 1. Before that, so we're going to assume that C1 is equal to C. Remember, C is the limit after we've continued this and the number of chains stop decreasing. So at that state, we can start from there. So that will be our initial state. I want to show that once we have this, then we definitely must have had our solution. So the assumption is that after this first value, that every subsequent move we make will still have the same number of chains. Okay, so now we'll look at two cases. So case 1. So in this first case, we are going to look at when we have the chain of interest, the chain that contains the Kate coin, if it is already at the left end. So if our chain of interest is already at left end. Okay, so for once we have this, it means that we have for instance, let's say it's an A chain, it could be a B chain. We already have something like this where we have one as the first position up to Kate's position. We could have more A's, so we have at least this as a beginning. Okay, so this means we need to have at least K of these A's, so therefore we must have that K has to be less than or equal to N. And based on the range we are dealing with, we also know that K is greater than or equal to N, so this means that K has to be precisely N. And once we have K is N, we see that this is all N of the A's, and we are done, because the rest will just be the B's, which will be the other string. Okay, so we move to the next case, the remaining case. So this time the string of interest is not on the left end, so just write this as otherwise. So what does this mean? It means that they have to be a different chain at the left end. So if this is our chain of interest, say we still use A to denote this, it doesn't have to be A. If it's B, we could just change everything alternatively. Okay, so let's say we have a K somewhere here, then we need to have something to the left. Okay, and the immediate part before this string has to be B, so there must be a B chain before the A chain. Okay, so now once we have a B chain before the A chain, we're going to show that we can't actually have anything beyond this, because if we need to have something else beyond that as well, it will have to be a B chain. So if we have a B chain, A chain, and then B chain, like this, and the A chain is a chain of interest, as the Kate coin is somewhere there, they will have to move this all the way, and then these two B chains are going to merge. And once these two merge, it means that we'll have one less B chains without increasing any other chain. So the C2 is going to be either C1, at least it's going to be less than C1, so it's going to reduce by 1. So this contradicts the fact that we've already chosen C1 to be at a stable state. Okay, so based on this, it means that the chain of interest is at the right end. Okay, if it's at the right end, then suppose it's not so suppose is not of length n, because if it's of length n, then we are done. We'll have length n on right end, and then the remaining n coin will have to be of the same type on the left end, and then we are done. So suppose we don't have this, we hope to get a contradiction. So we see that if you don't have this, we see that it implies that there exists another chain of same type. Okay, so now I'm going to label these chains as so starting from the right as T1, T2, T3, and so on. So this is the chain that contains the kth one is at the extreme right. This will be of a different type, so these two will be of same type. So we have at least this much. Okay, so from this might continue like this up to some T, let's say M. All right, so what's going to happen is this first one contains the kth, so in the next step we're going to have T1, Tm, T3, T2. So for this number of chains to remain the same, it means that these two have to be of different type, and we necessarily need to have M is even. Okay, and next we have that, so next we're going to have that okay, so next we're going to have that since based on what we're dealing with, we're already in a stable state and there are only two cases. The first case, it means that we already have N on one side, N on the other side. So any other case, each time we come, we must end up having, no matter which part of the process we meet, must end up having exactly the kth one being at the chain of the extreme right. So this means that the next kth one will also have to be at the extreme right, meaning after this we make one more step, we get this up to T3 and repeat the same again, so the kth must be here. So this is going to be the problem. So for what we did before, that's when we're dealing with the second case, we saw what it took. We saw what it took for the kth one to be at the extreme right. Okay, which is that we need the length of that chain to be at least this much. Okay, so we're just going to use this. So this means that the length of, so I'll use the length of T1. Length of T1 is at least 2n minus k plus 1, and the length of T3 is at least 2n minus k plus 1. And so it means that if you add these two lengths, they are of the same type, so it has to be at most n, will be greater or equal to 4n minus 2k plus 2. Okay, so we just simplify this. We get that 2k is greater or equal to 3n plus 2, and so k will have to be greater or equal to 3n over 2 plus 1, and this will contradict the inequality we have for this case. So it means that this is a contradiction, so it means that we have to have the opposite of this. So therefore the chain at extreme at right end is of length n, and we get two chains, one on the left, one on the right, both of length n. We're done. Okay, so that brings us to the end of this problem. I hope you enjoyed, so I'll see you in the next one. Bye.